But all right, so not sure about that, but you can see, like, if you're setting this up, if you are, you know, like programming whatever like interface you use with this radar or something like that, you certainly would need to be able to understand this and understand how it's working together. So this is all some stuff that certainly could be applied. It's also something that I feel like you're going to have a pretty cool job and be pretty smart to be able to apply this, which might be some of you one day. Because I have a pretty cool job. I get to come to school and teach you guys every day. But I don't get to, like, sometimes I wish a little bit that maybe I'd done something where I would be somewhere figuring all this stuff out. It would be pretty cool. But I did not, and I'm okay. I'm happy with that decision. I like where I'm at. But you know how parents, like whenever they were like the football star in high school, they live vicariously through their kids and try. So that's what I want to do with all of you guys. I want to teach you the math that I know, and I want you to take it and go do really cool math jobs one day, and then come back and tell me about it, and I can, like, feel so proud, like my little students are going out, like, yeah, are going out and doing all kinds of cool stuff. So I'm going to live vicariously and have all kinds of cool math jobs through all of my students. So if you do get a really cool math job, please come back and tell me about it, because I would love to hear about it. Cool jobs, still come back and tell me about it. But
relatively cool.
Yeah. I mean, jobs in general are cool. Hunter sometimes can be so aggravating, but then sometimes he's so hilarious. The other day, we got home from school, or maybe it was it was on Sunday. We did not go to church because my husband had been sick, and we didn't want to, risk anything there. So we just laid around the house Sunday. We were lazy, we didn't do much. And so Hunter, I realize it's 3:00, and he still has pajama pants and he's not put on any clothes all day. I don't think Henry even put on clothes. I think he just ran around his house in his underwear all day. But I said something about it. I was like, we have not done anything. We've been so lazy. Hunter says, Mom, this is just my unemployed look. So I have restrained myself from asking some. I've been seeing a lot of students coming in with a little bit of the unemployed look here lately. I'm not going to put on pants today, yeah. Hey, but work from home is starting to be a thing, so maybe that is employed. I don't know. But so, anyway, that's off topic. But anyway. All right, so we have a right triangle here. So our setup for this is x squared plus 6 squared equals s squared. Be careful with that s as a variable. I really don't like using it, but they did here. So I just gave a quiz in Math 1, and there was a kid who missed the whole problem because his s turned to a 5 halfway through his problem, and his 4s was a 45. I gave him partial credit, but okay, derivative. What's it going to be?
2x dx over dt plus 12.
So this is just 36. What's the derivative of 36? 0. So you don't have to put that there, but I'm going to just to let us know we took that through.
Y over dt.
Not y. ds over dt. Yes. So s is actually almost. S is decreasing at a rate of 400 miles per hour. So this is the rate of s. So ds dt, because it's decreasing, is going to be negative 400 miles per hour. And they tell us S is 10. We're looking for speed of the plane, which is our dx dt. That's what we're trying to find. Kind of dx dt. We're going to think about that in a second. We can plug in our 10, but we're going to be missing our x. How do we find our x?
The Staggering Theorem.
Staggering Theorem. So we'll have x squared plus 36 equals 10 squared, which is 100. So x squared is going to equal 64. So x is going to equal 8. So we'll have 2 times 8 dx dt equals 2 times 10 times negative 400. So we got 16 dx dt equals negative 8,000. We'll divide by 16. And our dx dt is going to give us, is it 500? Yes, 500. Negative 500. How do I measure that? Miles per hour. Now, technically here, what did the question ask for? Speed of the plane. So, speed does not have direction. What we found here is actually the velocity of the plane because it has direction. It's negative here. So the speed would just be 500 miles per hour. Now, when it really becomes a crazy problem is when your altitude is not constant. So, in this case, the plane's just flying at a constant altitude. But if your altitude's not constant, then this has to be a variable also, and then things become much more complicated. It depends on what type of question they ask you about here. We could do it here as long as they gave us enough information. They'd have to give us like altitude and the rate the altitude is changing at for like certain times. So if you were just doing like all variables, I think it would be more like a Calc 3 problem because Calc 3 is multivariable calculus. So it is when you are doing calculus, but instead of having an x and a y, you have an x, y, and z. So 3 variables. Depends on what you're majoring. Yeah. All right. So let's go now to the notes for today. Here's another cool problem that I like. Now, once again, I'm serious about this. If you guys go get really cool math jobs one day, please come back or just send me an email telling me about it or something. If you can't come up. Yeah, like tell me about it. Send me some math problems you've been solving. I want to see it. Although it's probably going to be very like your high level stuff is probably very computer and coding based like stuff. I would imagine, but I could be wrong about that. But I just want to know about it because, like, in this particular instance, we have a camera. And this camera is 2,000 feet away from this rocket that is going to launch into the air. And so, as this rocket launches, you want the camera to follow the rocket, right? And so, depending on what you're dealing with, it seems like the ones on TV, they kind of start off sort of slow looking, really, to me. It seems like they almost like hover for a little bit before they take off. And we're talking about like space shuttles that are going into outer space. But especially if you think of like launching, just like have some of you guys done like launch like just small rockets before. They go pretty fast and you can miss it really easily, right? And it's really easy. I know whenever I had Daniel Shosh, they had some project they were doing, I think in aerospace maybe, where they launched a rocket and stuff, and they invited me to go watch their launch, and it like messed up halfway, and then the wind caught it, and the second parachute didn't deploy or something. Anyway, that rocket was never found, and then I spent the next couple days feeling like the October Sky movie was going to come true to us, and that like somebody's house caught on fire because of their rocket. But thankfully, no small or large fires were reported anywhere around Elk in the next couple days. But what is that from Ted? Yeah. See, like you need Ethan. Okay. So, like, Ethan needed this device right there because, like, as you watch it, you see the rocket go up, but you don't follow it, right? So, in order to capture this perfectly, it would be nice.
Well, I thought she said that word after I did that. Like, I thought she don't say
It's all right. All right. So, you want the camera to be following the rocket, right? All right. So, it tells us here, in this case, a television camera at ground level is filming the liftoff of a space shuttle that is rising vertically according to the position equation S equals 50t squared. So one of the reasons it seems like the rocket takes off slow is because it's accelerating. So it is getting faster and faster as it goes upward. So this tells us the height of the rocket. S equals 500t squared. So somewhere somebody's already done some math to figure out that is what's happening to the height of this rocket here. And S is measured in feet. T is measured in seconds. They tell us the camera is 2,000 feet from the launch pad. We want to figure out the rate of change of the angle of elevation of the camera at 10 seconds after liftoff. Because what's going to happen, what you need to know so that you don't miss it, is you need to know the rate your camera needs to be changing its angle so that it catches it. So Ethan's video, minus the profanity, was actually a very good example because, like, in the video, the rocket took off, but the camera did not follow it, right? Because it's too quick. It's hard to do. So if you knew this, it could be programmed to do it correctly and catch it for you, because a lot of times there's lots of instances where human reactions are not fast enough to do things, but we can have technology set up that will do it for us, like photographing lightning and like all the sensors that they put on cars for like automatic braking and things like that. They can catch that faster than humans can react to it. So our equation that we're dealing with here is going to be tangent. So you can see they gave it to you here. Tangent of theta is going to equal S over 2,000. There's that S variable again. I really don't like it when I use it because they labeled it that. I don't know why they didn't call it H for heights, but they didn't.
40% of a bathroom pass down. You got elevation.
Oh, I do. I have elevation. Why is that not?
No, Tom, you're right.
Why is that a word? Oh, it is. Oh, never mind. It is. It is underlined there. Okay, so all right. Let me save this so nobody can get it. All right. So we need to take the derivative of this. Derivative of tangent is secant squared theta. What have we got to put with this? D theta dt. All right. S over 2,000 is the same as having 1 over 2,000 times S. So when we take the derivative of this, we're just going to get 1 over 2,000. It's just S divided by 2,000 is the same as having 1 over 2,000 times S. So you got an exponent of 1 here, 1 times this, and then decrease your exponent by 1. Okay? So that's going to go away, but what do I need over here with this?
Something over dt.
ds dt. It's whatever variable you were taking the derivative of. It goes on top. Okay. So I know that this is 10 seconds after liftoff, which means that's time, which is t equals 10. I don't have a t. I do have a dt, but I can't plug that in there. So, but they gave us this formula right here. S equals 50 t squared. So, if I know the S, then I can find the theta, and I can also take the derivative of this and find my ds dt as well. So let's do the ds dt first. Take the derivative. This is going to be ds dt. I will get 100 t times dt dt, but do I have to write that if they're the same? Not if they're the same. So I don't have to write the dt dt because that would just be 1. Right, this is in this case, because we're taking the derivative with respect to time, t is the variable that we're taking the derivative with respect to. So we don't have to put the dt dt because it's the same variable.
So can
Right.
now plug in the 10?
Now we can plug in the 10. So ds dt, whenever this equals 10, is 100 times 10, which will give us 1,000. So ds dt is going to be 1,000. We want to find the rate of change of the angle of elevation, which is d theta dt. That's what we're looking for. So we're not going to replace it. But we do have to know theta. So to find theta,
Divide by 6.
we are going to have to go back to the original equation, which is tangent of theta equals s over 2,000. What is s going to be 10 seconds after liftoff?
50 is 1,000. Hold on.
Not 1,000.
5,000.
It's going to be 5,000.
1/2.
Because to find s, we plug into our s formula, right? So we'll do 50 times 10 squared, which will, because we're wanting s here, not ds dt. And so we got 50 times 100, which is going to give us 5,000. So we can say tangent of theta equals 5,000 over 2,000. Yeah, it's just 50 times 10 squared is what we're doing there.
No, just, yeah.
This one's pretty bad, but it's just a 5,000 right there. 50 times 100.
I can read it.
That's not because
Okay. All right. Okay. So how do I solve that to get theta?
you divide by 10.
Can't divide by 10.
Get the derivative.
Nope. We don't want d theta.
On the calculator.
Okay, that's a good question. Opposite, although I'd use the word, instead of opposite, I would use the word inverse. What is the inverse of tangent? You're going to do inverse tangent of both sides. So we end up doing inverse tangent of 5,000 over 2,000, or if you just want to type in 5 over 2. Oh, let's see. Let's hit that green button before we hit enter. I get 1.19029. That is not a degree. That is radians because we're in radian mode. Everything on the AP exam is going to be in radians, so we're going to stick with radians. Occasionally our book throws some degrees in every once in a while, but let's stick with the radians here. So theta is 1.19029. And so we're going to plug that in up here. Secant of 1.19029. And this is secant squared of that, d theta dt. Now, secant squared, we can't really type into our calculator very easily. What is secant? Is 1 over cosine. So it's 1 over cosine of 1.19029. And you'll square it after you do that. It should equal 1 over 2,000 times 1,000, which is just going to give us 1/2. Oh, and sorry, my d theta dt disappeared there. So 1 divided by cosine of that number right there. It's going to be this. We must square it. So we get 7.25 d theta dt equals 1/2. All right, questions so far?
I understand all of it except for like knowing the secant square is thing.
Except for knowing that derivative first. You just have to yeah. All right, and then we just divide by 7.25. So d theta dt is going to be whatever we get whenever we do that. Divided by this answer. And so we get 0.069. What are our units? All right, theta. What's theta stand for? It is seconds. But theta is our angle. What are we measuring that angle in?
Degrees.
Not degrees. Because we were not in degree mode on our calculator. It is radians. So this is 0.069 radians. No, per second. What? It could go either way. It's okay. Okay. Questions? So at that point, you're moving up at 0.069. Now, if you were like programming something for this so that it would do it automatically, then you could actually like this is at that particular place, but if you were programming it, you could, have sort of like a systems of equations here where you have your ds dt over here is 100t. You could plug it in so that the computer was like adjusting as time goes along, so it's going to start off slower and then move up faster, or maybe not because of the distance. Certainly, the speed definitely increases as it goes up. But, once it's really high up in the sky, I guess it depends on how far you're zoomed in on it. You also got zoom to worry about, but like certainly when it's really high in the sky, you just got to look up and you'll see it, right? Yeah, but it's gonna be like a dot. But if you zoom in really as close as you can, then it makes a big difference. Yeah. Yeah. So it would be different. Mm-hmm.
I'm sure.
I think I am recording. I'm pretty sure I'm recording.
There's a function on like really fancy games that lock on. They probably like have this program.
Yeah, I'm not sure if it does like motion sensors and stuff too could come into play, which might actually be a little bit different here. But I'm sure all that stuff has like crazy math behind it too. All right, here's another really cool one. Anybody in here like work on cars, like car engines? A little bit, Daniel? Okay, so it might be necessary for us to watch a short video. Anybody, how many of you feel like you understand like how a four-stroke combustion engine works? Okay. Okay, several of you, but lots of us are not. All right.
I can describe it perfectly right now.
All right, tell us, Noah.
Oh, well, okay, so the process is suck, squeeze, bang, blow.
Yeah.
He's talking about an engine.
Yeah.
Here,
That's just the process.
he is exactly right, though. All right.
A four-stroke cycle engine.
Okay, let's watch this, hopefully. I usually try to preview my YouTube videos. Surely this one's not gonna... I had one, but I don't have it saved here. But you can
A four-stroke cycle engine is an internal combustion engine that utilizes four distinct piston strokes: intake, compression, power, and exhaust to complete one operating cycle. The piston makes two complete passes in the cylinder to complete one operating cycle.
Oh wait, sorry.
720 degrees of the crankshaft. The four-stroke cycle engine is the most common type of small engine. A four-stroke cycle engine completes 5 strokes in one operating
This is
cycle.
not the best video.
Intake, compression, ignition,
We're
power,
gonna-
and exhaust strokes. That is the basics of how a four-stroke engine works.
Let's see if
The
you
first stroke,
okay,
called
here we
the
go.
intake stroke. The crankshaft pulls down the piston by
Also called...
the intake valve is open
Yeah.
at this point in the cycle, and the air will be pulled through the intake manifold into the motor. After this is complete, the camshaft rotates to the low spot on the lobe. This allows the valve spring to close the intake
This
valve.
is a bad video.
The second stroke is called...
Alright, so it fills in with gas.
This is because it compresses
No,
the fuel/air mixture. While this is happening, the intake and exhaust valves are closed. The third stroke is called the power stroke. Right before the piston
Bang.
crankshaft reaches the top dead center, or known as the TDC, the spark plug fires. This ignites the fuel-air mixture, which then forces the piston downward. In the motion of the piston being propelled downward, the crankshaft is turned. This is the only cycle where power is produced. The fourth and final stroke is called the exhaust stroke. Once the stroke begins upward, the camshaft opens the exhaust valve, and the piston is propelled upward by the crankshaft, pushing the burnt fuel-air mixture out of the first stroke.
Alright, and then
Bad video.
I want to add to that. So one round of those four things is a round in your car. So when you see the rounds per minute,
Yeah.
that's how fast that car is.
Yeah. And those are in thousands.
Revolution.
Those are in thousands too. So when you on your RPM meter on your car, whenever it's